watch this. If I have the sine of theta, I'm not going to use x, equals 1/2, and I want to solve for theta, what that means is I need this sine thing, whatever it is, to go away. Well, it's clearly not multiplying, right? It's operating on this angle, but it's not multiplying times, so I can't simply divide through by sin, right? That would just be, don't make me, sinful. All right, so anyway, what I need to do is I got to make this thing go away. And the way that I do that is I go arc sine of both sides. What I do to one side, I must do to the other. Well, the arc sine of the sine, these guys cancel out. That's what inverses are for, to undo things. Arc sine of sine, gone. Guess what? Theta's by itself. Sweet. That's the thing that I wanted to get rid of. I wanted to solve for theta. So I got theta equals the arc sine, or the inverse sine, of 1/2. Now, we can answer the question originally. What this really said initially was, think about that. Arc sine of 1/2 is exactly the same thing as saying the sine of what angle is 1/2. Well, we know what the sine of what angle is 1/2. It's pi6. This implies that theta equals pi6 as opposed to pi halves. Watch out for my dyslexia. It'll flare up. All right? Now, you may say, but wait, Ripley. Well, wait. Don't I also know that the sine of 5 pi6 equals 1/2, right? Because if I go on my unit circle, right, and I go, I know that at pi6, I get √3/2, 1/2, and my y value is my sine. But oh no, over here, this is when, I wrote too small, didn't I? Theta equals pi6. But way over here, don't I get negative √3/2, positive 1/2? And this happens at theta equals 5 pi6. You're absolutely correct. But the arc sine can't spit out that value because it only has the ability to spit out values between negative pi halves and pi halves. This function can only spit out values between negative pi halves and pi halves. And watch, if I stumble up here and I'm saying the arc sine of 1/2, that means I'm going over here to 1/2, and I go up to my function right here, and I stumble over here, and guess what? That's pi6. For me to be able to get to this 5 pi6 value, think about what I would need to be able to do. I would need to be able to go way up here and have this function wrap back. And then that would happen up here at 5 pi6. Not allowed. As soon as this function wraps back, guess what? Horizontal line test, dead. Thank you for playing. Okay? Now, that right there is the inverse sine. Now let's write a couple of things up. Let's make sure that we understand this. In class, we're going to do a million of these. I'm just giving you the theory behind them right now. The most important thing that we understand is these two properties happen. The first is that the arc sine of the sine of x is always equal to x as long as x is between negative pi halves and pi halves. Now, we'll play with what happens if that's not the case. In other words, if I'm taking the arc sine of the sine of 3 pi fourths, well, what are we going to do? Well, I'll explain that to you down the road. The other is that the sine of the arc sine of x, the sine of the arc sine of x is always equal to x so long as x is between -1 and 1. Now, think about this. Let's just let me give you one real quick example just about something that's crazy here. Let's say that I want to take, I'm going to change colors. I don't know why, I just feel like it. I do what I want. If I want to take the sine of the arc sine of, actually, let's even keep it simpler than that. Let's start simple. What if I say the arc sine, if I'm trying to find the arc sine of 2. And I'm going to let that equal Now, remember, what this really means is that this guy right here is some angle, right? This is an angle because I can rewrite this. I can always rewrite this as the sine of which is always an angle, right? I plug angles into sine, cosine, tangents, secants, cosecants, and cotangents, is equal to 2. The sine of what angle equals 2? Well, there is no such angle. It doesn't exist because I know sine only goes between -1 and 1. It's impossible for the sine of an angle to equal 2. And that plays in to why these rules are in place. Now, why do we need the additional rules? You know, with my other trig, or with my other functions back in the day, I just knew that f inverse of f of x equaled f inverse of x equaled x. And that was always true. That was so long as f inverse was a function. Now, we had to turn f inverse into a function. We had to provide more structure for it to be a function. Remember back here, we had to steal the portion of sine that was 1 to 1. And as soon as we had to do that, as soon as we had to say, well, it doesn't really work, well, it works as long as we qualify it, well, then we have to qualify when this is the case. All right? That's arcsine. We're going to move on to arc cosine and arctan, or inverse cosine and inverse tan here in just a second. Okay, so once we have arcsine, it's real easy to get arc cos and arctan. Inverse cos and inverse tan. So now we're going to figure out what f of x equals inverse cosine of x looks like. Now, we're going to use exactly the same process, except we have to remember, you got to recall that that cosine looks like this. So I drop this guy down like this. All right, so this is f of x equals cosine of x. Okay, now what we're going to do is the exact same process. See, cosine is not 1 to 1, so its inverse is not a function. However, all I'm going to do is I'm going to steal this first little chunk that is 1 to 1. Now remember, this here is pi halves, and this here, and this here is pi. Okay, so exactly like we did with the inverse sine, we're just cheating. We're stealing a part of the function that is 1 to 1. Now, let's name these points real quick because this will give us a little bit of focus. This is 0, 1. This is pi halves, comma 0. And then this point down here is pi, I'm going to steal this point, is pi, comma, -1. All right, so when I go to sketch y equals the inverse cos of x, let's see what happens. Remember, to sketch an inverse, simply switch x and y. Okay, so instead of 0, 1, I'm going to put 1 out here. Let's see. I got to get out to pi though, don't I? You know what? I'm going to cheat just a little bit. Since we're going to end up all the way up at pi, I'm going to bring this down just a touch. All right, hopefully we won't screw this up too badly. All right, so this, I'm going to let this be 1, comma 0. So I took 0, 1 and flipped it to 1, comma 0. 0, comma pi halves. So I'm going to put pi up. Let's call this pi, just for giggles. All right. So 0, comma pi halves. That's going to put me about right there. All right. So 0, comma pi, and then -1 up to pi. All right. So that goes. Let's see. Did I get those right? No, I missed it just a touch. Just isn't going to look very symmetric. Sorry, guys. You gotta. This is kind of touch and go. So over here, guys and gals, don't mean to be gender biased, and up to pi. Okay, now remember, I should be able to reflect this across the y-axis, or excuse me, across y equals x, and these things are going to be reflections of one another. So if I take this thing and I go like this, whoops, and I go, whoa, like this, and like this, you see what happens there? All right, so if I were to sketch, you see how this is a reflection of this function right here across y equals x. Now, that's it. For exactly the same reason that we couldn't, remember how we couldn't wrap, I often have students say, well, Ripley, why don't we wrap this part? And why don't we wrap this part? Because if I do that, I'm going to wrap over here and wrap over here, and I lose my function because I failed the vertical line test. Okay, now, let's look really, really closely at this. We know this about the domain of cosine. We know that it's all reals from negative infinity to infinity. Stick any angle in, and I can give you a value out. I know that its range is from is from -1 to 1. Right? I got to get focused today, huh? Is from -1 to 1, right? However, since we're only taking this sliver right here, don't we know that this really is no longer the case? I'm taking the chunk from 0 to pi. I'm taking that 1 to 1 chunk from 0 to pi. I still have the same range, which is nice, because when I use that, when I stick it back in here, I know that this thing's domain, this guy, this inverse cosine function, is the same as the range. So I go from -1 to 1, which we can look at it and tell that, right? I mean, if I were to shadow this like glass, it would fall on the x-axis from -1 to 1, right? I know that its range is from 0 to pi. Now, oops, I keep doing that. Those should be brackets. Now, think about that for a sec. What that means is that arc cosine of anything can only spit out values between 0 and pi, the first two quadrants, very much similar as the arc sine, or the inverse sine, can only spit out values in the first two quadrants. I keep doing that, excuse me, in the first and the fourth quadrant, from -pi/2 to pi/2. All right, now they're different because we grabbed different parts of the function. Remember, with the arc sine, with the inverse sine, we grabbed that sliver that went through the origin, right? But for this guy, we need the first two quadrants. For the arc cosine, we needed the fourth and the first. Now, what does that tell us? Real simple. Remember, yet again, I don't mean to bore you, but remember, f of f inverse of x equals f inverse of f of x equals x.